Today we are going to be discussing Gauss's law on a uniformly charged infinite plane. Gauss's law is the law relating to the distribution of electric charge to the resulting electric field. Gauss's law is a general physics law which can be applied to any closed surface. In this situation, charge will be present in both sides of the plane. Unlike other closed, solid shapes like a sphere, because the plane is flat and geometry is symmetrical, there is a charge present in both sides, with half the charge on one side and half the charge on the other side of the plane. The charge density in this particular scenario is the surface area density on each side of the plane and is given as sigma. This can be assumed to be 2 times 10 to the power of -6 coulombs per square metre, and it is a constant. Gauss's law here can also be used to find the electric field, which discharges or emanates from both sides of the plane. The equation initially is given as the integral of the electric field strength multiplied by the area is equal to the charge inside divided by epsilon naught, given epsilon naught is a constant, which is 8.85 multiplied by 10 to the power of -12 coulombs per Newton meters.
Electric field will emit directly perpendicular to the end of the circular surfaces. No flux is emitted through the curved surface due to electric field lines being parallel to this surface. Therefore, the area of concern are the two ends of the cylindrical Gaussian surface. To find this area, we simply use the formula for area of a circle. Area equals pi r squared.
Now that we know our Gaussian surface is circular and we are using 2 pi r squared to calculate this area, sub the equation for area of a circle into our original formula of the electric field strength times the area equals the Q in over the epsilon 0, which gives us the electric field strength times area, which is 2 pi r squared, equals the surface density minus area over epsilon 0. This equation then simplifies to the electric field strength equals the surface density over 2 times epsilon 0. And this equation gives the magnitude of the electric field strength. Once we sub in our values, this leaves us with an electric field strength of 1.13 times 10 to the 5 Newton per coulombs. For the direction of the field strength, the electric field lines are perpendicular to the plane and thus to the top and bottom of our Gaussian surface. The field lines are directed downwards through the bottom of the box and upwards through the top of the box. In other words, they always point out of the box. No field lines pass through the sides of the box. Hence, the total area through which flux passes is equal to 2A, which is the area of the top and bottom of the box. The total charge enclosed is equal to the charge density times the area of the plane inside the Gaussian surface.
In conclusion, it is able to be summarized that for an infinite sheet of charge, the electric field of the Gaussian surface, which in this case is circular, will always be perpendicular to the sheet of charge. As the electric field is penetrating through the sheet of charge, this means that only the surface area for the two ends of the cylinder are going to experience the electric flux. To calculate the flux flowing within the Gaussian surface, we must multiply the area of one end of the cylinder, pi radius squared, multiplied by the surface density of the material, all divided by epsilon naught. An infinite sheet of charge is an important aspect when it comes to exploring the use of Gauss's law and is used regularly throughout modern day physics. Thank you for watching. I hope you enjoyed the show.